So, in the 24 lectures so far, we discussed how these semiconductors are different from metals and insulators. It's all about band gap, large band gap insulators, small band gap or no band gap metals, and then a sizable, a particular range of band gap gives this material semiconductor, which is so important, so much of electronics revolves about it, just because we can control the conductivity with a good resolution by doping. So, as the technology for doping is very, very advanced, and we can manipulate in the scales of a few tens of nanometers, let us say, the capabilities of all these devices, the semiconductors, become enormous. We have just seen that just diffuse p-type and n-type impurities in the same wafer and you get Pn junction, and that Pn junction gives you so many applications. You have a voltage regulator through Zener breakdown, you have light emitting diodes, you have solar cells, you have photodiodes. So many applications come out of just if you dope p-type and n-type impurities in that semiconductor. Now, the next set of devices or next range of devices are possible because of another kind of structuring where we dope two p-type and 1-type or two n-type and p-type in the same wafer and get what is called transistor. So, our next few lectures will be on transistors. So, let us first look at the structure. Transistor. So, you start with let us say n-type material. Suppose this is n-type semiconductor. This whole wafer is n-type semiconductor. In the picture it may look very large, but the actual things may be a few hundred microns, less than a millimeter. And then you diffuse say p-type from top and make it p-type like this. So, p-type is diffused, p-type impurities are diffused from here. So, this becomes p-type, you get a Pn junction, and then further diffuse n-type impurities from top and make this as a n-type. Let us say this is n-type. So, I further diffuse these donor impurities to make this as n-type. So, this was already n-type and this is p-type and this is n-type. So, now I have three kinds of impurity distributions, the donor impurities here, acceptor impurities here, and again donor impurities here, and here are two junctions. Here are two junctions. This is one junction. This is one junction. This is one junction. You have p-type on one side and n-type on other side. So, you have Pn junction. And then you have another Pn junction which is here. This is another Pn junction. So, you have a p side here, n side here, and then you have junctions. So, all those Pn junction characteristics will be here. At each of these two junctions you will have depletion layers. At each of these junctions you will have let us say everything, depletion layer, then you will have diffusion, then you will have electric field, and this diffusion will be related to concentration gradient. All these things we have done. And the drift current, electric field will give rise to drift current. So, drift, all that minority carrier, majority carrier, injection, forward bias, reverse bias, everything is same, and that's why I had said that if you understand Pn junction, you understand almost everything of semiconductor electronics. So forward biased, reverse biased, all that Pn junction characteristics that we have studied will be here and will be here. And this combination becomes so important. It gives rise to a transistor, and transistor can do many more applications than a single Pn junction. So there are some geometrical and doping characteristics to make it a transistor and give it a properties of transistor, and that is this middle region, this P here. Okay, by the way, this is called NPN transistor. This is called NPN transistor. And most of the time to transistor. And most of the time we will be using NPN transistor to explain all the physics, all the processes in the transistor. But you can have the opposite of this. You can start with a wafer which is of, to start with, the whole thing is P type. This whole thing is P type. Then you diffuse N type from one side, and suppose this is N type, this is N type, and then you diffuse again P type, stronger concentration, so that you get this P type here, and then you get PNP. So this is PNP transistor. Okay. But most of the time we will be using this NPN to describe all the physics and all the processes, and the only difference between this and this is all the direction of currents will be inverted, and all the polarities of the batteries that you connect, that will be inverted. Otherwise the remaining thing is almost the same. And if you talk in terms of majority carrier, minority carrier, the same sentences, the same language can be used for this and for this. But if you use electrons and holes, then of course the language for this and language for this will be different. What you call electron, in this case you will be calling holes, and vice versa, and so on. Okay. Now there are some characteristics or some names first. First some name. This sandwich layer, this layer, this region, this region, this is called base. This is called base of the transistor. So you have three regions. You have three regions, 1, 2, 3, 1, 2, 3. So this middle one, the one which is sandwiched between two semiconductors with same kind of doping. So that sandwich region is called base. Then one of these two is called emitter, other is called collector. So one is emitter and other is collector. You will have metal contacts. You will have metal contacts. You will have a metal contact somewhere here. You will have a metal contact somewhere here, and you will have a metal contact somewhere here. So that all three can be joined to the external circuit. Okay. So you will have three terminals to join to the external circuit corresponding to base, corresponding to emitter, corresponding to collector. So that is, this is the nomenclature. This is how we name it. What is the difference between these three? This is of course sandwiched, but this is on the two sides, so, and of the same kind, n type or n type, but there is still a difference. So three things are there, and each will have different characteristics, and let me name that. So base, the first thing is, the base is very lightly doped. And emitter is heavily doped. And collector is moderately doped. So doping concentrations, that is different for these three cases. Base is very lightly doped. The concentration of impurities in base will be, say, 5 to 10% of that in emitter, and collector will be little less than that. So that doping levels are different, and therefore you cannot interchange emitter and collector because their doping levels are different. So you cannot interchange these two, although on a diagram it may look that okay, both are same. So if you have this kind of structure NPN, and if I take this middle portion and rotate it by 90 degrees, I can show it like this. So this is that sandwich layer, this is that N, this is that N. So NPN transistor. Okay, so this should be very, very thin. How thin? Could be a micrometer, just 1-2 micrometers, or even less than a micrometer. So that is very, very thin as compared to this. These may be 100 times more than this. So this is one. Okay, we will come to that geometrical parameters. Doping level, this is very lightly doped, and one of these two, which is emitter, is heavily doped, and the other is moderately doped. So that is one. And the second is the geometrical parameters, the thickness. Your base is very thin of the order of a micrometer, whereas emitter and collector are relatively much larger, okay, maybe 100 times of this, or 500 times of this, or 200 times of this. So this is wide, and in this also collector is somewhat wider than emitter. And there is a purpose to it, right? That is why the transistor is transistor. That is why transistor is so important. That is why transistor can make so many useful devices, because of these parameters that people have searched for and created such kind of a transistor. Okay, so the symbol for Pn junction, you remember, Pn junction also we had symbol, this kind of symbol. And then the symbol itself tells that this side is P and this side is N. Similarly, for transistor, the symbol is, generally people draw a circle. Sometimes you may not draw, but good to draw a circle. And then 3 lines for these 3 parts, base, emitter and collector. So the baseline is, let's draw a baseline. So suppose this is base. Let me draw this as the base. So this line is base, and then 2 slants line, one like this, another like this, 2 slant lines. So this is the kind of symbol of this transistor, and these are the connections from where it has to be added to the external circuit. And this one is base, this one is base. And one of these is emitter, another is collector. And how do we distinguish which is base and which is collector? Here in the symbol, we distinguish emitter and collector by putting an arrow on the line corresponding to emitter. So if I put the arrow here, that means this is the emitter and this is the collector. And arrows can be put in two ways. I can put the arrow like this, or I can put the arrow like this on this line. And that decides whether it is a symbol for NPN transistor or a symbol for PNP transistor. So if I put an arrow here, this is NPN transistor. This is symbol for NPN transistor. And if I put the arrow in the other direction, if I have two lines coming like this, third line coming like this, this is base, and then this is emitter, and this is collector. And if I put an arrow like this, this is PNP transistor. And how do I remember this? That if the arrow is coming from base to emitter side, then it is NPN, and reverse is PNP. Little bit of physics will help in remembering this. And what is that? And that is, in normal operations with transistors, the base emitter junction. Okay, if you think of this diagram, if this is P, this is N, this is P, this is N, and if this is base and this is emitter, then the junction here, the Pn junction here between emitter and the base, right? Or if you use this diagram, this is N, this is P, and this is N, and if this is base, and if this is emitter, and if this is collector, then we are talking of this Pn junction here between emitter and base. And in this diagram, this is base line, this line is for base, and this line is for emitter. So this junction between base and emitter, this Pn junction. Okay, so this is very important result, and you should always remember this in normal operations. This base emitter junction and junction means Pn junction is forward biased. The base emitter junction is forward biased in all kinds of applications that we will be using, or in general, base emitter junction is forward biased, and this is valid for PNP junction transistor as well as NPN transistor. So both kind of transistor, this is valid. Okay, then the arrow shows the direction of current at this junction. So if you have a PN junction, if you forward bias it, okay, the P side is connected to the positive of the cell or higher potential, and N side is connected to the lower potential. This is forward biasing. And how does the current flow? The current flows like this. So inside this junction, the current goes from P side to N side in forward biasing. Reverse biasing, opposite. Okay. So this arrow on the symbol of transistor shows the direction of current at this junction. That means it should be from P side to N side. And so it is, if this is NPN transistor, then this is N, this base is P, and this emitter is N. So at this base emitter junction, the current should flow from P to N, that means from here to here, and therefore the arrow is like this. And if it is a PNP transistor, if this is P, this is N, and this is P. If it is a PNP transistor, then at the base emitter junction, if it is forward biased, what will be the direction of current? From P to N, and this is P. This is P. Emitter is P type and base is N type. So in forward bias, the current should be from P to N, and therefore the arrow is in this direction. So that is how the arrow is decided. So this is the symbol. And then if you look at a physical transistor, this will be done in a very small area of a millimeter or less than a millimeter, like that. Then it will be put in some protective covers and all that, and then you will have 3 contact points, 1, 2, 3. 3 contact points coming out. So I showed you a PN junction, and there are 2 metallic connecting leads were coming out of that, and now I will be showing you a transistor from where 3 such leads will be coming out, 1 for base, 1 for collector, and 1 for emitter. And before doing further physics, I will be showing you one application which is very interesting using a transistor, and this particular experiment is very widely shown by science communicators in science shows and in hobby classes, electronics hobby classes and all that, and it's all available at internet. The basic idea of this circuit is very old, say 3-4 decades old, but this particular circuit that I am going to show, particular application that I am going to show, without explaining what it is, you just see what kind of thing it can do, a transistor can do. So here you can see a transistor. This is a kind of its cover, its cap, its container. The transistor is well inside it, and then you can see there are 3 leads coming here, 1, 2, and 3. And this face, if you can see, this is a flat rectangular face, whereas if I rotate it and show you the back side, this is a cylindrical, half cylindrical curved surface here. Okay, so this kind of casing is made, one side flat and other side that is cylindrical, half cylindrical, and of course the top and bottom are flat, and from one top or bottom, whatever you call, the way you write, from there these 3 leads are coming, this one, this one, this one. And the data sheet will tell the middle one, if you face this flat rectangular part towards yourself, that middle one will always be base, and the 2 side ones will be, one will be emitter, one will be collector, and the data sheet of this will tell which side is emitter, which side is collector. You also have high power transistors. This is a low power, for small currents it is used, and then you have other kind of transistors where the casing is metallic, and then it is a full cylindrical type of thing, and from the bottom there are 3 leads coming out, and in that circular cross section or the top, there is a notch there from which people find, okay, this is the first lead and this is second lead and third lead, and then the data sheet will say which is emitter, which is collector, and which is base. So this is it. So I will just show a particular experiment with this transistor. So we have added 2 clips here, and then let me tell the other part of the circuit. This is a handmade coil of copper wire, and you can see there are 3 terminals coming out, here, here, and here. How can a coil have 3 terminals? What we have done is this 30 turns total. So starting from here, we make 15 turns, and after 15 turns are over, the same wire is taken here, and then this part is taken out, tap, central tap, and it continues. Again we go for another 15 turns. Okay. So, the ends of the coil are here and here. This is a 30 turn coil, ends are here and here, and from middle when it was 15 turns, at that time we have just taken that wire out and then continued. So, that is how that the third terminal is made. So, let me connect this battery to this transistor and these coils. So, I am connecting this terminal here. As I said, I won't tell you what is going on in this circuit, I just want to say that what kind of applications it can make. So, I connect this part here, the base part, this is the base part, I am connecting the base part here, then I am connecting this this most probably collector part here, and then the other terminal of the battery, the negative of the battery here. Okay, my circuit is complete. Is there something happening? Seems there is nothing happening, but then look at this another apparatus that I have. This is another coil, another 30 turns coil, and then LED is connected to this coil, and if I bring this LED here, see what happens. Can you see? Can you see this LED is glowing? And if I take it up at a distance, see what is happening? See what is happening? Take it down, see what is happening. If I place it here, see what is happening. If I place it here, see what is happening. If I place it here, see what is happening. And if I place it here, or let me place it like this, see what is happening. If I place it here, see what is happening. So, how there is a current in this coil? It is not connected to any circuit. Okay, it is not connected to any circuit, but still you can see there is a current out here. So, how the current comes here? You must be remembering that Faraday's law of induction experiment, where you pass a current in a coil, primary, secondary, transformer principle, mutual inductance, whatever you say, you pass a time varying current here, and the time varying current produces a time varying magnetic field, and when you bring this other coil here, the time varying magnetic field gives you time varying flux, magnetic flux, and the time varying magnetic flux creates an EMF, and that drives a current, and therefore it glows. So, that means you have a time varying current here, some kind of an alternating current here, but I am only using a single cell, it is a DC 1.5 volt. So, how come a DC 1.5 volt cell is able to create an alternating current? So, that means this is converting this DC to some kind of AC. Some kind of AC, not exactly AC, but some kind of AC. Some kind of time variation is very much there, and strong time variation. Only then it can produce enough magnetic flux and change in magnetic flux to give rise to this LED current. Okay? So, it is just a demonstration what things you can expect from transistors. So, although this particular circuit is very cleverly designed, but this is one of the applications of transistor, and we will be talking more about it, where it converts DC into AC. And this is important. We all know that when our power supply in household goes off, there is a power shedding, load shedding, then we use inverters with a battery. What is this inverter doing? This inverter is taking DC from the battery and converting into AC, and then our fans and our television sets, they work. Okay? So, this kind of circuit is called oscillator circuit, right. So, oscillator circuit, it can give you an oscillatory waveform from a DC. There are other applications. The main application in fact of transistor is in amplification, amplifying a signal. I am speaking, but then I am not speaking very loudly, but then an amplifier can amplify my voice, and then hundreds and thousands of people can listen it together. So transistors are used primarily for amplifications. Okay, so in next lecture we will do more physics, how the current goes in base, in emitter, and how the connections are done, how the biasing is done, and then later on we will talk of applications.